We'll be starting the session in 5 minutes.
Guys, we'll be starting at 5:35. Am I audible? So, hi all, welcome to your fourth AA Club Summer School session. I am Ashit from IIT Madras. Me and Nishita will take today's session. Today's session will be about classification. So, classification is used for classifying things. So, I'll give you an example where you can use these algorithms to get your task done. Let's say you have emails containing spam in it. So you don't want to waste your time looking at these spam emails. So in that case, you can use this classification algorithms to get your task done. Today I'll be taking naive Bayes as well as SVMs, and Nishita will be covering KNNs. So let's start with today's session. One second, I'll give present it. Naive Bayes is an algorithm which is based on Bayes theorem. You guys I hope you guys went through the video which I have sent in the WhatsApp channel as well as Teams. Most of you would have learned it from your school classes, but I'll give you a brief idea what Bayes theorem is in next slide. So Bayes theorem is used to determine a probability when you are given the other three probabilities. So in in this classification, while performing this classification, you'll see that we'll be able to determine these three probabilities, but our final probability only would be used for classification. So P of A here is probability for A, P of B is probability for B, P, P of B such that A has occurred is represented using this notation. Similarly, probability of A such that B has occurred is represented using this notation. So this statement, this expression over here is Bayes theorem. So you'll use it for doing classification. So basically, naive Bayes, there are two types of naive Bayes. One is multinomial and the other is Gaussian. So I'll be saying each with an example, and I'll work out the probabilities and do the calculation so that you'll be able to understand it much better. So we'll start with multinomial naive Bayes first. So multinomial naive Bayes. Coming to multinomial naive Bayes is used for classification when there are discrete features. So we can use this algorithm to classify whether text is spam or not spam. So we'll see it in depth in the next slide. Yeah, when we got a message like dear friend and we want to classify it whether this message is spam or not spam, mathematically we want to determine two probabilities. One is probability for the message being not spam, such that the given message is dear friend. And we need to determine one more probability, which is probability for the message being spam, such that the given message is dear friend. When you determine these two probabilities, if this probability, if it's greater than this one, we'll classify the message as not spam. Because since the probability of the message being not spam is greater than the probability of it being spam, we'll classify it as not spam. Else, we'll classify it as spam. So our multinomial algorithm will revolve around calculating these two probabilities. So first, in training phase, we'll determine in Bayes theorem, you have four probabilities, right? So I'll show you the theorem once again. So this is what we need to determine. And these three probabilities, we'll get it from the training phase. So in training phase, we'll calculate those three probabilities. I'll tell you how we calculate that. So in training phase, we'll have samples in not spam dataset as well as samples in spam dataset. So these are the statements in not spam dataset. The statements are hi, friend, dear, friend, lunch, give money, which is there in the not spam dataset, as well as money, money, friend, dear, take money. These messages look like a spam message. So these are present in the spam dataset. So we'll see how we calculate the three probabilities. So probability for a message being not spam is given as 4/6. How we got 4/6 is from the data set. So we have 4 samples over here. In total, we have 6 samples, 4 in the not spam part, 2 from the spam part. So when you do 4/6, you get the probability as 0.66. Similarly, for probability of spam, we'll get a value of 2/6. Since 2 come from spam, and in total we have 6. So we have calculated these two probabilities. So then the next is how do we calculate this probability? Probability of dear being present in not spam. So we have calculated it to be 1/7. So this comes from the data set. So dear is present only once from the 7 words 1, 2, 3, 4, 5, 6, 7. Since dear is only present once, it is given a probability of 1/7. And for in spam dataset, we'll see how many times dear is present. We have 6 words in spam dataset, out of which only 1 is dear. So the probability would be 1/6. Similarly, we'll calculate all the probabilities. For all words, we'll calculate the probabilities with respect to each dataset. So we'll get in training phase, this is what our algorithm will do. So let's say in testing phase, you get a new word, which is dear friend. How do you calculate the two probabilities and classify this message? So we'll apply Bayes theorem. We need to determine this probability of not spam, such that the message is dear friend. So according to Bayes theorem, this expression would be this one: probability of dear friend being present in not spam times probability of not spam by probability of dear friend. So this expression comes totally from the Bayes theorem. You guys can check in place of A and B. You guys can put in place of A. You guys can put not spam, and in place of B, you can put dear friend and check. This would be the resultant equation. And probability of dear friend. Since the message given is dear friend, probability of dear friend would be 1, as the given message is dear friend. So this term would turn out to be 1. And in turn, we'll have probability of dear friend such that it's in not spam times probability of not spam. And from the multiplication property in probability, we'll split probability of dear friend present in not spam as probability of dear present in not spam times probability of friend present in not spam, and times probability of not spam. So our final equation would be in this form. So where do we get these 3 probabilities? We'll get it from the training probabilities. So we have the probability of not spam over here, which is 4/6, and probability of dear such that it's present in not spam is 1/7, and probability of friend such that it's present in not spam is 2/7. We'll substitute those probabilities in this expression and calculate a final value. So this is how you calculate probability of a message such that it's in not spam. So we'll get a probability value for not spam case. Similarly, for spam case, when you write the same equation for spam case, it would be probability of dear such that it's present in spam times probability of friend such that it's present in spam times probability of spam. And when you substitute these values from the training probabilities, you'll get a value for spam case also. So comparing these two probabilities, since not spam probability is more than spam probability, we'll classify this message as not spam. So this is how multinomial naive Bayes works. First, we do the training using our training data sets, calculate these respective probabilities, and when we get a new example, we apply Bayes theorem and get the final expression and substitute the probabilities from the training phase. We'll substitute the probabilities that we got from the training phase, and while calculating these two, we'll get two values. If one value is greater than the other, we'll classify it as, if the not spam value is greater than spam value, we'll classify the message as not spam. Else, we'll classify it as spam. So this is basic working of multinomial naive Bayes. So for you guys to try out, I have an example. You can try for the message lunch money money. I have given all the probabilities in the Slido question. You can go to slido.com and use the code 2909400, or you can scan this QR code. I'll go to the Slido window. You guys can see the QR code, right? So it's similar to the dear friend case. We need to calculate probability of not spam such that it's lunch money money. Such that the message is lunch money money. For spam case also, we need to calculate the same. So we have been given probability of lunch such that is present in not spam, probability of money such that it's present in not spam, and so on. So you can use these probabilities to determine the final, whether it's there in spam or not spam. So I'll give you an int. It's just multiplication of the corresponding class. As you saw in the previous case, it was just multiplication of all the resultant equation was a multiplication of those three terms. So when you get a probability to be not spam probability to be greater than spam, you put it as not spam, or else you'll put it as spam class. I'll give you guys 2 minutes to attempt the question. You guys can refer the Bayes theorem equation, or else you can see this this equation, the final equation, how it looks. It's basically probabilities of individual words times the probability of class. I'll give you guys the expression if you're not able to get what the final expression is. The final expression for the not spam probability would be this probability times this probability, the whole square. Money is present twice in the message. You guys have to notice that one. And times probability of not spam. This would give you the not spam probability, which would give you this whole probability. And for spam, you do the respective terms again, you'll get this probability. I think it's 2 minutes. I'll lock the voting and show the results. Let's wait for 120. Yeah. Yeah, most of you had answered it to be not spam. Yeah, it's correct. So I'll show you why it's not spam. I'll show you the solution for the problem. So in this case, we had got a message called lunch money, and we had to classify whether it's not spam or not spam. So probability of lunch such that it's present in not spam was given in the Slido question as 1/7. For money, it's given as 1/7. You should note that it's been squared because money is present twice in the message. So when you multiply this, you'll get a number greater than 0. And for the spam case, when you do the multiplication, you would get it as 0 because probability of lunch present in spam is 0 as lunch was not present in the spam dataset. So this message is classified as not spam. But there is a problem because lunch, since it was not present in spam, our training dataset, since it was not vast, lunch was not present and it was given a probability 0. So this was unfair for the spam class. So there is a technique called Laplace smoothing, which we'll apply to tackle this issue. As you can see, this lunch money message seems to be spam, but we have classified it as not spam. We'll see how to tackle this issue in the next slide. Yeah, there's a technique called Laplace smoothing. Even if the word is not present in the data set, if it's present in the counter data set, let's say the word lunch is not present in the spam data set, but if the word lunch is present in the not spam data set, we would consider that the word is in vocabulary and we'll add 1 to it. So no matter if the word is present or not, the frequency of the word being present would be taken as 1. If it's present like 5 times, it would be increased to 6. And the total probability and the denominator would be plus the unique words in vocabulary. So I'll give an example like how it works. Since let's go to the previous case. Yeah, for the word, let's say lunch is not present over here, but lunch, by applying Laplace smoothing, lunch would be taken into consideration because it is present in the vocabulary. Since the vocabulary contains lunch, as you can see in the not spam dataset, lunch frequency of 1 would be taken and it would be divided by the number of words in the spam dataset. So when you calculate the final probability, this won't turn out to be 0, and in turn this would be greater than this probability. So this time lunch money, which seems to be a spam message, would be correctly classified as spam. So that is how Laplace smoothing is used in multinomial naive Bayes to get the correct output. So we had discussed about multinomial naive Bayes, which is used for discrete features. So in turn, Gaussian naive Bayes is used for continuous data. So Gaussian naive Bayes is used when we'll have a continuous distribution of values, numerical values. Let's say you went to watch a movie. Let's say you have a data set of people who went to watch a movie, and you have the amount of popcorn they ate. So that is a continuous data. So we'll see how the continuous data is used in calculating probabilities. So there is a curve here which is quite popular in artificial intelligence. This is a normal distribution. This normal distribution you can notice this widely in artificial intelligence. We'll see the properties of normal distribution in the next slide. Normal distribution will contain, this is the function equation for normal distribution. So in this, you can notice 2 unique terms, which is mean and standard deviation. Most of you would know mean from your school classes. It is nothing but average of the given numbers. Similarly, there is a formula for standard deviation too. Standard deviation intuitively tells how the data is dispersed around the mean. whether it's broadly dispersed or whether it's narrow. The standard deviation, a number, when you apply the formula, you get a number, and that number would tell you how the data is dispersed. So this is the normal distribution formula. You guys don't need to memorize this formula. You can just look up in the internet. This formula, you don't need to know the formula to understand the concept. It's just given for reference. And standard deviation too, the formula is not important. The computer would do the task for you. You just need to know that what standard deviation means, and it's present in the normal distribution formula. So we'll see how normal distribution functions are used in calculating the probabilities for continuous data. So we have a data set, which as I told you before, we want to classify whether a person likes the movie or not. How can we do it? So we have collected a few features, which is the amount of popcorn the person ate in the movie, amount of soda the person has drank in the movie, and the amount of candy the person has ate. So we'll use these three features to classify whether the person likes the movie or not. So similarly, we also got data for the person who did not like the movie and amount of various snacks he had eaten in the movie. So this is for the person liking the movie, and this is for person not liking the movie. So we have certain numerical features over in this column. You can calculate the mean by just summing up all the values and divide it by the number of values present in the column. So when you do that, you'll get the mean. And for standard deviation, similarly, there is a formula. So you use the numerical features to calculate the standard deviation. When you calculate the standard deviation as well as mean and put it in this equation, you would get the normal distributions. So since there are three columns and two each for each, and one each for each class, you would get 6 distributions. So 3 columns and you have 2 classes. So you'll get 6 distributions to calculate the probabilities. So this is what happens in Gaussian naive training phase. In training phase, you take the data, calculate its mean, standard deviation, put it in the normal distribution function, get the normal distributions, and save it for testing phase. When you get a new sample, what you do is you will plot the x coordinate in the graph and get the y coordinates for this x coordinate. And for liking the popcorn, this would be the y coordinate. This y coordinate would give you the probability, which will be used later. And this x coordinate will also give the probability for not liking the popcorn also. So similarly, we do it for the soda pop as well as candy, and we'll get 6 probabilities. We'll see how these probabilities are used for classification. And there is one more feature I want you guys to understand. Why is the red graph for popcorn behind the green graph? It's because you can see the mean. The values for the red graphs are very less. So when you calculate the mean, it would be very less, and in the x axis, the graph would be much behind. So for the green case, since the mean value is more, this would be front in the graph. So this is just an intuitive understanding of the normal distribution. Since we had got the graphs and we also have a sample for testing. This is the sample which we'll test now. Whether for this sample the person likes the movie or not. So by applying Bayes' theorem, similarly, it is similar to the multinomial case. We would multiply all the 3 probabilities times the probability of the person liking the movie. When you do this, you'll get 2 probabilities for like case as well as does not like case. These probabilities you would get by getting the y coordinates of the graphs. For the liking the movie case, you would get 3 probabilities, which you would substitute here. And this probability of likes, would be determined by the number of samples of likes in the data set. This probability is determined by number of person liking the movie samples by total samples. This probability is given by that. These three probabilities, you would get it from the normal distribution. So when you substitute the values, you would get two probabilities. If this probability is greater than this probability, then it is classified as person liking the movie, or else the person does not like the movie. So this is basic working of Gaussian naive bias. And there you will also encounter one issue when you calculate these probabilities. The probabilities value will be very small. The nature of normal distribution is such that whichever value which is far from mean would be given a small value. So, and this will lead to underflow. Our computer won't be able to store that one. So how would we tackle underflow in probabilities? What we do is we don't multiply the probabilities. We just take log of the probabilities and multiply. So taking log helps in tackling this issue. So why log helps in tackling this issue? Because it's due to the log property. This is log graph. You guys can look, if you guys don't know about log, you guys can look into various resources and understand it. For this, for understanding multinomial naive bias, you don't need to know the log properties and all. You just need to know that for lesser values of x, log value is more. So when you put small values of probabilities in the equation of log, you would get higher values, which in turn our computer can store. So that is the use case of log. So this was about Gaussian naive bias and multinomial naive bias. And why is it called naive? Basically, it's called naive because it assumes independence between the features. There is one more method for doing this type of classification, which is word embeddings, which is like an advanced technique in NLP. You guys would learn it in the upcoming sessions. This independence of features would lead multinomial naive bias to get the score for the word dear friend would also be same as the word friend dear, since it's just multiplication. So that is why the algorithm naive bias is called naive. So this was about naive bias. We can move on to the code implementation of naive bias. Let me go to the Colab notebook screen. Yeah. So in implementing multinomial naive bias won't be as rigorous as we have seen in the slides. It would be much easier because sklearn would take care of the job of calculating all the probabilities. We just have to give the input as we just need to give list of sentences as input and the target values, and multinomial naive bias in sklearn would do the job for us. So in this example, we'll import numpy pandas, which you guys have learned in your second session, and we'll import a data set. I hope you guys have received the data set. You guys can load into the data frame using read CSV method, and we also have imported quite a lot of things from sklearn, which is count vectorizer. I'll tell you guys what this does, and we have imported also train test splitting from sklearn. We have imported the model as well as a metric score, which will help us in determining whether our model is good or not. So in this case, in this example, we'll have a couple of statements, couple of news articles related to hockey, and couple of news articles related to space. So we'll try to build a model which will classify the news article, any news article, as whether it belongs to hockey or space. So first we need to do training. So for training, we'll load the data set from the CSV file. We'll split it into two. X contains the sentences and Y contains the target variables. So when you have splitted the data set, then next I'll tell you guys what count vectorizer does. Let's say our vocabulary has 3 words, which is, was, and that. So what will our count vectorizer return for the message that is? So basically what it does is the word is present twice in the message, and for in the vocabulary it's present in the first index, in the index given number 0. So since S is present twice, the count vectorizer would return 2. And for was is not present in the sentence, so it would return 0. And for that is present only once, so it would return 1. So why are we converting the messages into numbers? Because our model won't be able to understand English, and we have to give all the inputs in the form of numbers. And for that was similarly, in the place of that we'll give it a value 1, and in the place of was we'll give it a value 1 again. So this is how count vectorizer does. Basically, it takes the vocab and takes the message, calculate the frequency for each word, and calculates the multinomial NB probabilities as we have seen in the slides. So count vectorizer does that for us. So we'll vectorize the sentences, and we'll do train test splitting. I have kept test size as 0.3. That means 30% of the old data set would be allocated to test. Would be allocated for testing. And we define the model, fit our training samples into the model. And since our model has been trained, we'll predict it using dot predict method and pass the X test, which is samples we kept for testing. And we'll also evaluate the accuracy to test how our model works. So we'll pass the prediction as well as the true values. True values and prediction will pass it to the accuracy score function, which in turn would give you the accuracy. So our model has got an accuracy 99.83%. So I think our model performs fine in doing the classification. So now let's test it on custom data. So we'll pass a sentence related to hockey. The hockey game was intense and exciting. What this should do is it should classify the sentence as hockey class. And we'll also pass a sentence related to space. The spacecraft successfully launched to Mars. So this is a sentence which is related to space. So when you pass this new data to vectorizer, yeah, we are passing it to vectorizer because we need to convert this words into numbers, because our model only understands numbers. And we'll pass it to predict. We'll pass it for our model to predict, and we'll get the predictions as 0, first sentences of 0 class and for second sentences of 1 class. I think I told you that hockey is of class 0 and space of class 1. So our model is classifying correctly. It classified this to be as hockey and this sentence to be as from space. This was about implementation of multinomial naive Bayes. We'll see how to implement Gaussian naive Bayes. It's also similar, but since Gaussian naive Bayes is for continuous data, we'll import a data set which has continuous data in it. So we'll use iris data set, which contains measurements from flowers, Setosa, versicolor, and virginica. What and all measurements this data set contains is, it contains sepal length, sepal width, petal length, as well as petal width. And Setosa belongs to class 0, versicolor belongs to class 1, and virginica belongs to class 2. So we'll load the iris data set. The features will be loaded in X variable, and the targets will be loaded in Y. And you do train test splitting similar to the multinomial case. We define the model and pass our training samples so that our model would calculate the probabilities and make it ready for our testing phase. And when you pass the testing samples, it will predict the classes, and we pass it to our accuracy function to determine the accuracy score. So we got an accuracy around 97.78%. So our model has been trained well, and it performed pretty well on the testing dataset. So I picked a few flowers in internet which belong to Setosa and as well as versicolor. So this petal widths and sepal widths belong to Setosa, and this petal widths and sepal widths belong to versicolor. So when we pass this as a list to our model and predict it, our predictions would come out as 0 and 1. Let's check what 0 class belongs to. It belongs to Setosa and 1 class belongs to versicolor. So our model predicts it correctly. This belonged to Setosa and this belonged to versicolor originally. So our model did a good job in getting the predictions. So this was about a naive bias. If you guys have any doubts, you can ask me now. You can ask through either chat or as well as by raising your hands. So some guy has asked, he didn't get how vectorizer works. So let me show that. Sorry, this was. One second. Yeah. Vectorizers will have certain words in our vocabulary. This in vocab means whatever words that would be present in our training and testing training samples. So we'll get the what counter vectorizer does is when we get a sentence, it'll give the frequency of each word in the sentence. So for is, since it's present twice in the sentence, it'll give a frequency of 2. Since was present, it wasn't present in the sentence, so it's given a frequency 0. And for that, it's present only once in the sentence, so it's given a frequency 1. So this is what count vectorizer does. So one person has asked why when setting testing size to 1, why is it raising an error? Because you won't have any samples to train. Your model won't be able to determine the probabilities and get the values for testing phase. So you need to have ideal split is 80-20 split. You need to give at least 20% of the samples to testing and 80% for training. How did the need of using Gaussian name classification of flower, what is its advantage compared to multinomial case? So compared to in multinomial, it's discrete features, right? You will have either the frequency for each word would be would be a number, but for like flowers and all, it will be like in decimals, so it's continuous. So usage of Gaussian naive bias and usage of normal distribution and getting the probabilities would be a much better approach than using multinomial naive bias. How do we ensure that dataset used in Gaussian method is continuous? So if your dataset has like amount of popcorn, width of flower, so that would be so you can use Gaussian naive bias for that one. And when you have something like you need to classify whether a sentence is spam, so you can use multinomial in that place because words are a discrete feature. Attendance link would be shared in like 10-20 minutes. Yeah, Oki as 0 and space as 1. It is our wish. You guys can go to the CSV file and change if you want. So our model would behave the respective way. So Laplace smoothing is used for increasing the frequency of each word by 1. Let's say the word lunch was not present in our spam dataset, which led its probability to be as 0. So when you add, so that lunch money was not classified correctly. But when we do Laplace smoothing, your message would tend to get classified correctly because since earlier it was not present and you get the entire probability as 0. But when you add 1 to each column, you would tend to classify it correctly. That was about Laplace smoothing. So for a word not being in the dataset should not be the case of you classifying it as spam or not spam. So we are preventing that using Laplace smoothing. Prediction is only done for Y. I didn't understand your question. Yeah, prediction is done only for getting your class values. I hope that was your question. Whether it belongs to spam class or not spam class, that would be our prediction. So the prediction also would be in the form of numbers, 0 or 1. So if it's binary classification, it would be between 0 and 1. There was one term to divide in Neighbor's formula. Why didn't you use while? Yeah, that was a problem. I told you, right? 1 second, I'll show you the screen. So there was one term in the division, in the denominator, which would turn out to be 1 because I'll show you the screen. Yeah, this would be our ideal formula, but probability of message being dear friend is always 1, right? Because the given message is dear friend. So our denominator term would go to 1. That's how the division terms vanish. Multinomial NB, yes, you can use it for multi-class classification also. In this example, we only used it for binary classification. You guys can check out how to do the multi-class classification also. It's quite similar. So I think we'll wrap up doubts for now. We'll go on to next topic, which is support vector machines. Yeah, support vector machines. Support vector machine is yet another algorithm which is used for classification. Support vector machine, yeah, it's used for linear as well as non-linear classification. We'll see what this each term means. What is meant by linear, what is meant by non-linear. We'll see in the next slide. And it can also be used for regression and also for outlier detection tasks. In this session, we'll see how SVMs can be used for classification. One second. I'm not able to change to next slide. 1 second. Give me a minute. Yeah, I think it works now. Yeah, there is a concept called hyperplane in support vector machine. So what this hyperplane means is, so this is your features. You'll have feature A, feature B. You'll plot feature for each point, and you'll get a set of points like this. This red points belongs to one class, and green points belongs to the other class. So the basic idea behind support vector machine is that you would use a line or a plane in 3D case to split the samples, and when you get any other sample which will be plotted, and if it's on this side of the line, it will be classified as this class, which in that side of the line it will be classified as this class. So this is the basic idea behind support vector machines. So the dimension of the hyperplane depends on the number of features. For 2D case, it would be a line. This is called hyperplane. In this case, for 2D case, it is called a line, and for 3D case, it's called it will be a plane, because you will be able to split points of two classes using a plane in this 3D case. For a 1D case, the hyperplane would be just a point. So this is the hyperplane. This is how hyperplane's dimension will change when your number of features increase. So we'll see what is meant by linear as well as non-linear data. So linear data you'll be able to split using a line. So this is what linear data looks. But for non-linear data, you won't be able to split the points of different classes using a line. You need to use some other curve for it. In this session, we'll see how to split using linear as well as non-linear case. So before moving on to the how you determine the plane which separates both the classes, we'll see some definitions called support vectors and margin. What support vectors is that? It's a line which passes through the support vectors. So support vectors is nothing but the points of either class nearer to the hyperplane. So this is the hyperplane. So these 2 points are closer to the hyperplane. So the line passing through this is called the support vector. And for this class of points, this point would be the support vector, because this is the point which is near to the hyperplane. And one more definition is that what is margin? Margin is the distance between the two support vectors. So this is margin. So ideally, while training our SVM, what we want to do is we want to maximize this margin as much as possible. So that would be our main aim in support vector machines. Main aim would be maximizing the margin. So first we'll tackle the linear case, how we'll separate classes of various points using hyperplane. So for that, we need to represent our points in form of vectors. So I hope you guys also went through the vector video which I have sent, which covers the basics about vectors. If you are from 11th and 12th, you guys would know it from your school classes or else from your coaching. So W in this case is a vector which is perpendicular to the hyperplane. So this H0 is the hyperplane, which we would define it initially. W will be the vector which is perpendicular to the hyperplane. And what is X? X is the position vector of the data point. Let's say one data point is present over here. The line joining the origin as well as the data point would be the position vector. And we'll calculate the equation of H0 using this W and X. First, we'll do W dot X dot. While applying dot product, you can split this as magnitude of W, magnitude of X times cos theta. Cos theta is nothing but the angle between W and X. And you can write X cos theta. X cos theta is nothing but the component of X along W direction. This blue line over here is X cos theta. You can just replace that with another alphabet or variable C. And when you bring this W times X to the LHS and replace it using another variable B, you get the equation for the hyperplane. This is for any equation. This is the equation for a point present in the hyperplane H0. So we got the equation for the hyperplane. So we'll try. Our main aim would be optimizing the values W and B, so that we'll get a proper optimized line which has maximum margin. So W times X plus. So for the class of points above the hyperplane, from your straight lines chapter in math, you guys would know that for any point above the hyperplane, it would be greater than 0. When you substitute the points values in this equation, you would get this value greater than 0 for any point above the line. Similarly, for any point below the line, you'll get it as less than 0. So for these class of points, you'll get less than 0. For these class of points, you'll get greater than 0. And we'll also determine h1 and h2 equations. Earlier, we had determined h0 equation, which is w times x plus b equals 0. Similarly, the h1 and h2 equations would be w times x plus b equals 1 and w times x plus b equals minus 1. Why is it 1 and minus 1 over here? So it's basically our choice. You can rescale w and b values and make it 1. So when you calculate the center of these two lines, we would get the hyperplane equation, which is w times x plus b equals 0. So this is how we find the equation of h0, h1, and h2. We'll use these three equations and calculate the optimal line which separates our data points. As I told you, while determining the optimal line, we need to maximize the margin. So in order to maximize, first we'll calculate the margin. So margin, we can calculate it by, this is the margin, distance between h1 and h2. We'll calculate it using vectors. X minus is the position vector for this point, and x plus is the position vector for this point. Note that these 2 points are support vectors, and this point is also a support vector. So when you take x plus, when you subtract this vector from this vector, you would get a vector joining these 2 points. You would get a vector joining support vectors of one class and support vectors of one more class. So this is the vector joining these two support vectors. And when you take this vector's component along W, you would get the value for margin. So this is the length for margin. So we'll see how it looks numerically. So first we'll subtract the two vectors. We'll get this vector, dot it with W. But while dotting, we won't get the component of this vector along W. We'll just get the dot product value. When you divide it by magnitude of W, you'll get the component of this vector along W. So calculating the magnitude of this vector will give you the margin length. So when you simplify this, W times x plus is nothing but 1 minus b. This is 1 minus b because from this equation, any point on h1 would satisfy this equation. So here, in place of x, we'll substitute x plus, and in turn, we'll get w dot x plus as 1 minus b. Similarly, for the x minus case, you would get 1 minus 1 minus b. So when you substitute those values, you'll get the margin value as 2 by magnitude of w. So this would be our margin. So in order to calculate optimal values for W and B, we need to maximize the margin 2 by magnitude of W, which also means that we need to minimize W by 2. It's just the reciprocal. If you maximize this in turn would be minimized. And also, we not only need to minimize this, we need to also follow certain constraints which we have defined before. That is, for any point above the hyperplane, it is one class. And for any point below the hyperplane, it's minus 1 class. So so y times w times x plus b would be greater than equal to 0 for all points. Why is it greater than equal to 0 for all points? Because any point above the h1 would be, for that point, w times x plus b would be greater than 1. And since its y value is 1, this two product would turn out to be greater than 1. And for any point below the hyperplane, below the equation h2, w times x plus b would be less than minus 1. And when you take product of these two, you'll get the value to be as greater than equal to 1 for all data points. So our final optimization problem would be, we need to minimize this, plus we need to follow the constraint for all the points. So this would be our constraint optimization problem. When you feed this optimization problem into your model, it will calculate optimal W and B value for you. So you'll get the hyperplane equation, which will be used for testing. So in testing case, you'll get a point. And if you know that the point is on the one class of the hyperplane, you would give it a class number 1. Either you would give it minus 1. So that is how basic linear optimization works in support vector machines. You guys can scan the QR code. I'll give you 3 minutes, and you can also ask your doubts in the meantime in chat. 1 second, I'll present it so that you'll be able to scan the QR code. So I won't be able to look at the chat. You guys can unmute and ask because I'm sharing the attendance QR. 1 second, I'll check whether I'll be able to get the chat. Meantime, you guys can share the attendance QR and ask your doubts in the chat related to support vector machines. Or if you have doubts from neighbors also, you can ask in the chat. Is the link working? Is the link working? 1 second. Yeah, we have just enabled the link. You guys can check it. Check now. Is it working? I think it's working. One second. If you guys want the Google Form link, I'll share 1 second. Yeah, I think someone has shared the link. You guys can use this one. Guys, if you have any doubts related to support vector machines, what I have thought like linear optimization, you can ask me. It's basically you'll determine the hyperplane equation and you get the constraints margin value and optimize it by giving it to the model. So you'll get the ideal W and B values, which would separate your two classes. Random values will be generated by your model. You won't need to specify anything. You just need to define it. Why do we need to maximize the width? We need to maximize the width because you need to have as much space between both the classes. That is why we need to maximize the width. Class 1 is points above the points above the plane. Class -1 is for the points below the plane. So in SVMs, when they wrote the model, it was not given class 0, it was given class -1. So that is the change over here. W is nothing but any vector perpendicular to the hyperplane which we randomly define. there won't be any points between the margin because support vectors is the only points which are closer to the hyperplane. So if there is any points between the margin, that would become the support vectors. So I think it's enough for doubts. I'll start the next part, which is non-linear, just for non-linear case. 1 second. Yeah. So when you have in your training samples, when you have a noise, so noise is always present in your will be always present when you do artificial intelligence. So when you get a data set from a hackathon, it will always have some noise. So in order to tackle the noise, there is something called soft margin. Earlier we had hard margin. Earlier the constraint we defined is called an hard margin because all the points should satisfy the constraints. But over here we'll define something called soft margin. Even if a point is present in the region of the other class, it would ignore it and try getting the optimal plane. So that is how we tackle noise in linear data cases. Earlier, this was the constraint we developed previously. Y times W times X plus B greater than equal to 1. We'll introduce a new term called zeta, which would ease out the constraints in some of the cases. So for this point, zeta value would be in such a way that this condition would be satisfied. So that is how this soft margin works. So this zeta value cannot be any random big value. We need to optimize that also. So we'll put that in our loss function. And there is a definition for zeta in soft margin case. This is the definition. You guys don't need to remember it. You guys need to just get an idea like what is zeta and how is zeta defined. What is C? I'll tell the significance of C. Before that, you guys can see the definition of zeta. This type of definition would help our margin to act as soft margin. So when you put this expression in the loss function, you would get this final loss function. We are just substituting zeta with this equation. So for soft margin case, earlier our loss function would add only the omega square by 2. So why omega square? Like there is no problem in like squaring the magnitude. That's why that's why we are squaring it. So you can also have omega by 2 instead of omega square by 2. So it's just it leaves out your mathematical calculations in the next steps. That's why we are squaring it. And for soft margin case, we are adding this term over here. So what is the effect of C? So when C value is higher, you would the margin would act like an hard margin. So when this value when you give an I value for this, your model would tend to optimize zeta as much as possible, and you would get a hard margin. So when the C value is small, it will act like a small margin. So in your cases, when you see that your data that you got from the whatever website you got has a lot of noise. If you notice that one, you can use smaller C values because since it contains noise, so that would lead to optimal solution. So larger C value of C would lead to lower training error because it will overfit on training data, and smaller C value would cause higher training error and underfit on training data. So we need to get a optimal value for C by experimenting with the data and C values. So we have seen how soft margin works and in the previous slide. So what if we get actual non-linear data? So we need to be able to get a hyperplane, not in a line format. It should be any curve. So for this type of data, you can see that the hyperplane can be a circle, which would separate these two classes. So in order to get that, we'll use some methods called kernel method. So what kernel method does? So basically, intuitively, kernel method would map our lower dimensional data points into higher dimension. So here you can see that you can't split this points of different classes using a line. You will need a higher dimensional curve. So, but when you convert it into higher dimensions, you can see that you'll be able to separate these points using a linear plane. So that is how kernel methods help in classification. Yeah, it will map into higher dimension. In that higher dimension, you can apply your regular constraints and get the optimal values. So there are two types of kernel methods, polynomial and radial. We'll see in next slides. So you might think that mapping into higher dimension would increase our computation, but that is not the case. When we add the constraints and apply Lagrangian multipliers, you guys don't need to know the method. It's just the definition. You guys just need to know the final expression. So you guys don't need to know the Lagrangian multipliers method for understanding SVMs and all. You just need to know there is something called Lagrangian multipliers. And when you apply this method on the constraints, you would get an equation like this. So you just need to know some equation like this exists. So when you do this equation, as you can see, our final data points, it's not in the form of individual data points. It's in the form of dot product. So for getting the higher dimensional points, we don't need to get the individual points in higher dimension. We just need to get the higher dot product of them. And also this would contribute to our computational efficiency. So computation of dot products is much easier than calculating each point in higher dimensional space. And only support vectors alpha is non-zero. This is the key idea of SVM. So only support vectors would be used in determining the hyperplane. No other point is used in determining the support vectors. So in this dot product also, we'll use only dot products where there are support vectors. So that would ease out our kernel computation, and we'll be able to get the kernel. We'll be able to get the hyperplane. So that is how kernel works. Yeah. So for coming to polynomial kernel, this is the polynomial kernel function. When you put your coordinates of data points, this polynomial kernel would return data points in higher dimension. So this is the function for it. So what each term signifies in this function. So R is the coefficient of the polynomial. D is the degree of the polynomial. So a larger D value would increase your complexity of the curve. So when you have D equals 1, it will just be a linear line. When you have D equals 2, it will be like a quadratic function. Similarly, when it's D equals 5, it will be a much higher dimensional curve. So that is how your model complexity varies with D value. So as you increase the D value, it will also increase the complexity, as well as it will also lead to overfitting. So we'll see how this leads to overfitting in next slide. And also similar to the linear case, there is also a variable called C, which will lead to lower training error. Larger C will lead to lower training error, implying overfitting, and vice versa. So that is how these values affect these parameters that we define in the modeling case would affect your solution. Yeah. So you can see some points in this feature space. So for this case, we'll set t equals 1. So when we set d equals 1, the separating hyperplane would be a line. And in this case, we set d equals 2. So the separating hyperplane is a quadratic function. So when you d equals 5, the separating plane is a higher dimensional curve. So this is how your hyperplane varies when you change your d values and apply polynomial kernel. So this is the basic idea behind polynomial kernel. You provide the data points in your current dimension to the polynomial kernel. You'll return the points in higher dimension, and when you map these points and optimize it, you would get a function like this. So the optimization part and all would be taken care by the model that we define. Coming to radial basis kernel, similar to polynomial kernel, radial basis kernel also has its own function. You guys don't need to remember the function. You guys need to only know how the parameters affects the training. So that is the most important part, and also understand intuitive idea behind this formula. So x1 minus x2 computes the distance between the 2 points. So this expression would compute the distance between 2 points in this formula, and gamma gives us the influence of each training sample. So when you have low gamma value over here, this value would be diminished. So when let's say you have 0.001 and you have 100 over here, when you do the product, will be this whole value will become will become less, and the influence of this sample would be reduced. So higher gamma would increase influence of each sample and lead to overfitting. Lower gamma will lead to underfitting. This is an example on how the classification occurs when you have different gamma values. So for gamma equals 0.01, you can see the model is not classifying properly. So what this diagram means is whatever points in the yellow region is classified as belonging to yellow class. Whatever points present in the gray region is classified as black class. So that is what this figure signifies. When you have an optimal gamma value, it classifies it correctly. But when you have a higher gamma or higher gamma value, this would lead to overfitting. I think you guys can see the small gray circles over here around the black dots. So that means it overfits on the data. Whenever you get a point in between these 2 points, the model won't be able to classify properly. So the higher gamma value you set, higher the overfitting you will face. So you need to carefully select gamma values as careful as possible by testing it with your testing and as well as training samples. So I have a question for you guys. You guys can scan the QR code or go to slido.com, use 5945864 and answer the question. So this is the data points given. You need to tell which kernel you will use for classifying this type of data points. Go to the Slido, scan the QR code or go to slido.com, use this code and answer the question. Which type of kernel would be suitable for that data? So the data was 2 circles. So 2 concentric circles, and you need to tell which type of kernel would be used in this case. I'll give you 2 minutes to answer the question. So if you guys want to see the data, it's this. It's just 2 concentric circles. This orange belongs to one class and blue belongs to another class. You need to tell which kernel can be used to classify these 2 points more effectively. Like all the 3 kernels would be able to classify to some extent. You guys need to tell which kernel would be most suitable for this case. We'll wait till 100. I think 89 people have responded. I show the results. Yeah, most of you had answered it to be as radial basis kernels. So that is the correct answer. So for this type of data set, we need to use radial basis kernel. Yeah, that comes to the end of our SVM class. We'll see how these SVMs are implemented in code. I hope you guys can see the code. First, we'll implement odd margin SVM. Odd margin SVM, we can get odd margin SVM by putting IC values. You can refer to the slide, like what C values will give you odd margin, what C values will give you soft margin. So when you set higher C, the higher SVM would behave as an odd margin SVM. So we'll import matplotlib, sklearn, numpy. This is our data points. This is the x coordinate, this is the y coordinate, and this first definition of data points belongs to class 1. Second set of data points belongs to class 2. And np.vstack is a function to use to stack these two data points. So what this does is it will append these data points to the end of the list. That's it. And we'll set y equals class 1 for the first one and class -1 for the second class. So we got the x and y values for the training case for us to do our training. And we'll define the support vector machine, and the kernel is set to be linear. So first we'll see how to implement linear SVM. And C value is set to be large. Setting C value large implies it to be an odd margin. And when you fit the data set, our model would be trained, and you would get an optimal W and B values. Using model.cof at index 0, you'll get the W value, and model.intercept 0, you'll get the B value. And this code is used for plotting. You guys don't need to worry about this part of the code. It's just plotting our line and visualizing our model. So these are the points belonging to one class. These are points belonging to class -1, and these are points belonging to class 1. So our model predicts this line. So this would be our model would be correctly able to classify all. Our model was being able to classify the points. So this is for odd margin case. And what happens when we pass nonlinear data to odd margin case? So basically, when you pass nonlinear data to odd margin case, what I mean by nonlinear data is, let's say you have a blue point over here, or in this part of the space. So our odd margin algorithm won't be able to determine a point because that won't satisfy our constraints. So we determine certain constraints, right? The y times w times x plus b should be greater than or equal to 0 for all points. So when you have a blue point in this side of the plane, that won't satisfy the constraints, and our odd margin SVM would train for a long time and won't give you an output. You guys can change this value to be a small and put a nonlinear data to it, and you guys can test it. Yeah, I have got the nonlinear data. This is the nonlinear data. You guys can see you can't split these points using a linear line. I have plotted the points for you guys. And this cell has been commented. So when you run this cell, what happens is this would run forever and crash your runtime, because we have set a high C value for a nonlinear data. So when you have a data set and you want to classify it as classify using SVM, and you see that your data is getting trained for longer, that signifies that you need to set a lower C value. So setting lower C value would ease out the constraints, and your model would be able to train. So that is the inference behind this long training time. Coming to soft margin SVM. In soft margin SVM, earlier we had set it to be 10 power 10, 10 power 10. But in this case, we'll set it to be as C value to be as 10. Earlier we set it as e power 10. Now we'll set it as 10. So lower C value would ease out the constraints, and similarly we'll define the data point. This data point is similar to the previous definition. We'll define the model, and after training we'll get W and B values. And when you plot it, you'll get a curve like this. So this is how our soft margin SVM was being able to classify the points. So any point above this would be given class 1. Any points below this would be given class -1. You can see the plot legend over here. Class 1 is red, class -1 is blue. This is how soft margin works. Coming to polynomial case, we'll use a data set called make moons. This would give us a data set like this. So this would be a data set. It will make data set points like moon. So you set the sample, noise, random state, and initialize the classes. And when you fit your model, and this part of code, you guys don't need to worry. This is for you. This is used for plotting and visualization. Only this part of code is for the training. So if you guys understand till there, you are good to go. So this is for just plotting the points. So when you plot it, our SVM polynomial kernel SVM predicts this hyperplane. Most of the points would be correctly classified. Most of the points is correctly classified using this plane. You guys can play with these values, degree of the polynomial, C value, so that you'll be able to get a proper hyperplane which classifies these points 100%. So you guys can try out different values for degree as well as C, and try to make this curve to classify these 2 points also correctly. So that is related to polynomial kernel. Radial basis kernel. So in each case, you just need to change the kernel value and your parameter value. So that is it is simple when you use sklearn. And for this case, we'll use make circles dataset, and we will fit it to get the parameter values. And when you plot it, this is the plotting part of the code. Only the training and testing happens till here. So when you plot the code, you can see that you'll be able to classify the samples as one class if it's inside, and class -1 if it's outside. So this is how radial basis kernel works. I hope you guys understood about SVM and a bias. If you guys have any doubts, you can ask me in the chat, or you guys can unmute and ask. Let me see the chat. What is the best way to understand and apply these code implementations by ourselves? So code implementation for SVM case, is nothing but you'll set the kernel and you'll set the parameter values like C as well as degree. So I think it is just a one line of code. You need to just load the data set the values, set the kernel, train it. That's it. That is for the code part. For plotting, you guys need to look the matplotlib documentation and check how to do it. That is for the implementation part. I was disconnected, and can you please send the attendance? Yeah, attendance would be displayed again in the end of the session. You guys don't need to worry. Yeah, I think that's it from my side. I think Nishita will be taking KNNs. I'll answer your doubts in the chat meanwhile.
Okay, visible and visible, right?
Yeah, you are visible.
Okay, you guys can see the screen, right?
Yeah, it's visible.
Okay. So, hi everyone. I'm Nishita. I'm a coordinator here at the AI Club, and I'll be taking the KNN's part of today's session. Okay, KNNs. So, KNN stands for K nearest neighbors. This algorithm was formalized in 1967 by Thomas Cover and Peter Hart, and it served as the beginning for basic pattern recognition. So, this algorithm is also one of the oldest machine learning algorithms, and so it's a very simple, easy to implement, and it's a very intuitive algorithm. It's a supervised learning algorithm, meaning that it deals with labeled data, and it's used in both classification and regression tasks. So you saw what regression tasks were last class, right? So in regression tasks, basically the target variable or the output can take continuous values. But in classification tasks, for a given input, you have to predict a label. So that's how regression and classification tasks differ, right? So now how does this KNN algorithm work? So as the name suggests, it has something to do with the k nearest neighbors. K can be any integer, basically from 1 to any integer, right? So it will consider the k nearest data points to a test data point and classifies the test data point into the class which most of those k neighbors belong to. So it basically classifies the test data point into the majority class of those k nearest neighbors or k nearest data points. So the principle is that birds of a feather flock together, or similar things occur nearby. So that's essentially the gist of the algorithm. It's a very simple algorithm, like I said. So let's understand it like with a visual representation. Okay. So this circle over here is nothing but a test data point. That means the model does not know what class this circle belongs to. Or so it's a test data point. We do not know what class this circle belongs to. So you can see these squares. These squares are nothing but data points of class A, and these triangles represent data points belonging to class B. Now this model, this KNN model, this KNN model has to predict which class this circle belongs to. So let's consider K as 3. It'll consider the 3 nearest data points, that's 2 squares and 1 triangle, and based on that, predict the class of the circle. Okay, so you can see there are 2 squares and 1 triangle. Clearly, the majority is the square. So it will predict this circle to lie in the squares class or class A. Okay, so that's the algorithm. So it basically chooses the majority class. You don't have to restrict yourself to K as 3. You can even consider 5 data points, 6 data points, how many ever. Okay, so in this algorithm, the majority class amongst the K nearest neighbors is the class label of the test data point. But what is feature space over here? Feature space is nothing but the n-dimensional space where each dimension is a feature of the data set. So if there are n features, then it's an n-dimensional space. Okay, what is a data point? A data point is nothing but an instance of the data set. So in the data set, you'll have features or attributes and an output, right? So one row of that data set is nothing but a data point. So you can plot those data points into the feature space corresponding according to the features. So it's just like if you have say 3 features, then you have a 3-dimensional space, and you can plot your data points according to the values of its features. So essentially, how does this algorithm work? It basically works like a voting system, except the voters are only the k nearest neighbors. So that was about the algorithm, how it functions. So you can see like over here, I took the triangle to be the majority class when we consider 3 nearest neighbors. So over here, it will predict the circle to be lying in the triangle class because triangles are 2 in number and the square is only 1. But however, if you consider like 5 data points, 5 nearest neighbors, then it will lie in the square class. So that's how this algorithm works for classification. But how about for regression? So for regression tasks, it'll take the average value of the sum of all the target values of those k nearest neighbors, and that average value will be the predicted output by the model. So for each of these k nearest neighbors, they'll all have target values, right? So it'll sum all of them and take the average, and it'll return that as the predicted output. So that's how this model works for regression tasks. Good. Now, in this algorithm, there are some hyperparameters. Hyperparameters are nothing but the parameters that the user has to input. Like for example, the value of k. So the value of k should be given by us, right? We can choose k to be any number. And similarly, there's one more hyperparameter called the distance metric. We'll get into that. But first, let's talk about k. So k is nothing but the number of nearest neighbors or number of nearest data points we choose to consider for predicting the output. So you can obviously play around with different values of k, and the most optimal one can be chosen. But typically we use k, like we first there's a rule of thumb to choose k as the square root of n, where n is the number of data points. So, and also clearly you have to choose odd values of k, odd integers, so that you'll avoid ties in classification. For example, if you choose an even number of k, like an even value of k, say 2 or 4, then you can have exactly half half data points which belong to class A, and another half belonging to class B. So you'll get a tie over there, right? So to prevent that, you can choose k as an odd number. Okay, so what happens if you choose a very high value of k, and what happens if you choose a very low value of k? Both these values of k have their own fair share of pros and cons. Let's get into them. Okay, so if you choose a higher value of k, choosing a higher value of k is very good because you consider a large number of data points. And when you consider a large number of data points, you eliminate the possibility of you choosing some random outliers or random variations in the data set, which don't actually represent the data set. So that's something good. Your prediction is less affected by random variations in the data set. You don't consider outliers if you choose a large value of k. So that's good. But the problem is, like how we're choosing a very large value of k over here, like 20, you don't see there are some red data points over here, right? You ignore them. So if they're outliers, then you're good because you don't consider the random variations in the data set. But what if they too have some pattern or some intricate detail of the data set? Then you'll be overlooking those important patterns in the data set, right? Like what if these red data points over here actually have some pattern? Then choosing a higher value of k makes the model overgeneralize, or it makes it generalize too much for making a prediction, essentially underfitting, right? It'll have a very smooth decision boundary. You can see over here when we choose a very high value of k, essentially it'll cause underfitting. So you can choose a smaller value of k. But when you choose a smaller value of k, the decision boundary becomes a lot more complex because you're considering each and every intricate detail, each and every data point. Like when you choose 1, you're considering like essentially right next to that data point. So you'll be considering many outliers and noise in the data, and you will capture like many intricate details and patterns, but it comes at the risk of overfitting. So you'll have your model will be too sensitive to the noise, and when it sees unseen data, it won't generalize too well to that. It won't even it'll cause a lot of error, essentially overfit. So it'll underfit for higher values of k, and it'll overfit for smaller values of k. So keeping these two pros and cons in mind, you have to choose an optimal value of k. Good. So now coming to the other hyperparameter, that's the distance metric. Now, till now, when I say we choose k nearest neighbors, most of you would have thought nearest means the Euclidean distance. Like when you measure the distance between two data points, you have a Euclidean distance. That's just root over x2 minus x1 whole square plus y2 minus y1 the whole square. So you guys would be thinking that's what nearest means. Like if that's small, then that's the nearest distance. But that's not the only distance metric we have. We have different distance metrics that are used to measure the closeness or similarity or nearness in the data point, among the data points. So like essentially in this algorithm, the distance metric is used to measure similarity or closeness between the two data points, right? So the data points, essentially data can be a lot more different. Like you have numerical data, you can also have textual data. How can you use Euclidean distance for textual data? It makes no sense, right? So that's why there are different ways to measure distances, and clearly depending on different data sets, different data, the problem you're trying to solve can also be different. And there's another problem known as dimensionality. Basically, when you have a large number of features, or when you have a large number of dimensions, almost all the data points become equidistant from each other. So this is a phenomenon that occurs when we have a large number of dimensions. So using Euclidean distance over here can actually make no sense because almost everything will have the same distance, same value. So keeping all these reasons in mind, we have different distance metrics. They basically capture different aspects of the data and are accordingly chosen. So what are some of the distance metrics that we see? So mainly we have the Minkowski distance metric. So this is the main distance metric. So you can, what is this distance metric? So you see over here, xi is nothing but a data point and yi is another data point. Okay, so xi, I goes from 1 to n. So like x1, x2, x3 till xn, that's one data point. And y1, y2, y3, y1, y2, y3, that's till yn, that's one data point. So now what does this Minkowski distance do? So it basically calculates the absolute difference along each dimension. See, I over here represents one dimension, like I goes from 1 to n, so it represents all the dimensions, right? So this term is nothing but the absolute difference along one dimension. Okay, that will be raised to the power p, and all the dimensions will be summed up, and that will be taken to the root over p. So you'll take the sum and you'll raise it to the power 1 by p. So that is the Minkowski distance. Now, depending on different values of p, you have different distances. Okay, so you guys will be familiar with the Minkowski distance right now. So basically, it's just the absolute value along each dimension raised to the power p, and you sum up along all dimensions, and you take it to the power 1 by p. That is the Minkowski distance, and depending on the value of p, there are different distance metrics. So clearly, you're most familiar with the Euclidean distance, right? When p is equal to 2, it's basically xi minus yi whole square summation over each dimension. Like how many ever dimensions you have. That depends on the number of features you have. Now, next, another distance metric is the Manhattan distance, which is just p equal to 1. So when p is equal to 1, it's very simple. It's just the sum of absolute differences along each dimension. Okay, so now we have something known as the Chebyshev distance. So when p is very large, or it tends to infinity, when p is 1000 itself, we get something known as the Chebyshev distance. How does something like this become max of xi minus yi absolute difference? That means the maximum of the absolute difference along all the dimensions, the maximum absolute difference. How does something like this become something like this when p is very large or tends to infinity? Let's see. So when p is very large or it tends to infinity, you can see over here, this is the Minkowski distance. Now, when p is very large, what happens? Let's see. So let's take an example in which the absolute difference along each dimension between two data points, like along the first dimension, let's say the coordinates difference is 0.05. Then you have 1, then you have 32, then you have 15. So each of these will be raised to the power p. Okay. Now, like you can consider this as the if say n is 3, then you can consider this to be the difference along the x-axis, difference along the y-axis, difference along the z-axis. All of those are raised to the power p. Now, all of those are summed up and raised to the power 1 by p. So this is the Minkowski distance. What happens when p tends to infinity? Say like p is 1000. Clearly, this number is less than 1. It will become 0. It will tend to 0. Now, this will be a finite quantity. It will remain 1. When p is 1000, it will be 1 only. Now, we have 32 to the power 1000 and 15 to the power 1000. So, clearly, 32 to the power 1000 is far, far greater than 15 to the power 1000. So, 32 to the power 1000 dominates over all the remaining terms. Because even if you add 15 to the power 1000 to 32 to the power 1000, it's approximately only 32 to the power 1000 itself. Because this 15 to the power 1000 is negligible when compared to 32 to the power 1000. So essentially, you can neglect all the other terms because the largest term dominates, and that will be raised to the power p whole to the power 1 by p, limit p tends to infinity, which is nothing but 32. So in general, the maximum term over here, or the maximum absolute difference along compared to all the dimensions, will come as the final output. So this will essentially become this. So, or in other words, this Minkowski distance will become the maximum absolute difference amongst all those dimensions when p is very large. So that's what Chebyshev distance is essentially. Okay, so I'll repeat this once more. So basically, this is nothing but amongst all the dimensions, you have absolute differences, right? Like amongst the x, like if you have x, y, z coordinates, then along x direction, there's one absolute difference. Along y, subtracting the x coordinates. So you have to compare all the absolute differences amongst all those dimensions, and the maximum one will come as the output when p tends to infinity. because that will dominate the remaining terms. Adding other terms will become negligible. So you can neglect them. That's all. So now we can see there are other distances, like I've introduced Euclidean distance, Manhattan distance, Chebyshev distance. There are other distance measures like Hamming distance, which is used for strings or categorical data. We have cosine similarity and Jacquard similarity. So you can see this is how the Euclidean distance looks. So it's and this is how the Manhattan distance looks. This plus this. That's it. So that was about the distance metrics. So now sorry. Okay, so now let's understand some features of this algorithm. So we understood the hyperparameters of this algorithm, the functioning of this algorithm. Now let's see some features of this algorithm. So this algorithm behaves like, it does instance-based learning. So an entire instance of the data set is used to make a prediction. There's no separate training phase. Like at once, all the entire training data set is used and you make a prediction on the test data set, on the test data point. So that's why it's called instance-based learning. It's also non-parametric, meaning that it doesn't assume anything about the distribution of the data or how the data is, or the relation between the data and the output, like the input and the output. For example, last class you guys would have seen linear regression. So we assume that the output is related to the input linearly. But over here, there's no such assumption. There is a principle, like how the algorithm behaves is that it just uses closeness to determine similarity and it makes a prediction. That is a guiding principle of the prediction. It's not necessarily how the data should be. So this algorithm does not assume anything about the data. That's why it's called non-parametric. So it's not like linear regression. See, okay, then we have, it also does something known as lazy learning, meaning that it doesn't explicitly like learn something from the training data set. Okay, it uses it to make a prediction. That's all. So it doesn't explicitly learn anything from the training data. Okay, so those are the features of KNNs. But you can clearly see that this algorithm also has some drawbacks. Okay, so the curse of dimensionality. Like I've already said, dimensionality. So I've already mentioned dimensionality before, right? So when the number of features increase, you have a higher dimensional space. Now, when you have a higher dimensional space, almost all the points become equidistant from each other, and this degrades the performance of the KNN model, of the KNN algorithm. Okay. Next, we have class imbalance. Now, this is something that's very important. So I showed you examples of the square and the triangle, right? What if there are a large number of data points that belong to class A and very less belonging to class B? Then clearly, as this algorithm uses uses the majority, there can be a chance that it'll mostly predict the test data point to lie in class A, the majority class. So that's why if there is a class imbalance or too many outliers are also there, then KNN won't perform well. So class imbalance is something very important, like when one class is present in majority. Clearly, it'll tend to classify most of the test data points belonging to that class as belonging to that class. So that's why when class imbalance is there, it won't perform well. And one more very important thing is space complexity and time complexity. See, in this algorithm, we're measuring many distances between test data points and the train data points, right? We'll calculate all those distances. You have to store those distances, and then you have to compute the nearest, like k nearest, like 3 nearest or something. 3 nearest distances you're supposed to consider, right? So you have to compare all of them to find the nearest distance. So clearly, it's taking a lot of storage or space and a lot of time to compute, right? So this increases the space and time complexity of the algorithm. So when you have like large data sets, it'll take a longer time, or it'll take up a lot of space and time. So that's one disadvantage of this KNN algorithm. With this, we're done, but we have the code implementation left. So before that, I want you guys to answer this question on Slido. It's a very simple question. So what happens when we increase the value of k, basically taking higher values of k? Do scan this QR code or just type in this code in Slido and answer this question, guys. Okay, cool. So when we choose a higher value of k, what happens? I'll give you guys 2 minutes. You can even ask some doubts you guys have, if any. Okay, 1 more minute. Okay, so yeah, most of you have voted correctly. See, when we increase the value of k, the answer is option A. So when you increase the value of k, you basically cause the model to underfit. And what happens? You guys saw last session, right? What happens when it underfits? Bias increases and variance decreases. That's essentially underfitting. So that's why the answer is option A. Okay, so with this, we're done with the question, and let's go to the implementation part of it. So before I go into the code implementation, the actual code, I'd like to give you guys a gist of what's happening. Okay, what I'll do in the code implementation. So first, we'll load in the data set, the entire data, and then we'll split it into test and train. And test and train basically mean, yeah, the training data points, the model will already know what class the data points belong to. But in the test data set, it won't know what class it belongs to, and it has to predict the class of the test data points. Okay, then we provide the value of k or a bunch of k values if you want to do trial and error. And then you have to provide the distance metrics and weights. So what do weights mean? So sometimes when you choose larger values of k, you'd want to give more importance or more weightage to the ones that are nearer data points. So that's why you can set weights, and then you have to give the train data. You have to fit the train data to the model, and you have to provide the test data to the model. It'll calculate all the distances between all the feature vectors, and then it will select the k, like smallest distances or the nearest neighbors, and then it will determine the class of the data point, test data point, according to the majority class of those k nearest neighbors. And if you're going to do a regression task, then it will take the average, or if you have weights, the weighted average of those target values of those nearest neighbors. Okay, so that's how it'll do. That's the gist of the code implementation. So like for classification, it'll take the majority class, but for regression tasks, it'll take the average of all the target values of those k nearest neighbors, or it'll take the weighted average if you give weights. Like you can give weights as you can give more importance to the ones nearby. So now let's go into the code implementation. After the code implementation, I'll share the attendance QR code. You can scan it. Okay, so this is the code implementation. You guys can see the code, right? Should I zoom in a little bit more? Okay, so here I'm importing. So we're going to create the KNN model and see how it's performing on our test data set. Okay, so here I'm importing the libraries. These are, you'll see them as we go along. So from sklearn.datasets library, I'm importing a function known as fetch-openml. So this fetch-openml is a very important function that can be used to import datasets from an OpenML repository. So this repository has datasets that we can use. I'm using the famous MNIST dataset, which basically has a large collection of handwritten digits, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, till 9, 0 to 9. It'll have all of those handwritten images, right? So obviously these are a bunch of images. So their features, if you see the feature of this data point, an image is the data point over here, you'll see there'll be a bunch of, it'll basically be the pixel values of those images. Okay, so now I'm separating the data set into the features, into the variable X, and I'm storing the label, that's the category, 0, 1, 2, or 3 of those images into the variable Y. But I'm converting it using as type this. Using this, I'm converting it from categorical data to integer data type because it's better to work with the labels when they are integer. Okay, so that's what I'm doing. I'm separating out the label and I'm separating out all the features. Okay, into the variable X and variable Y. Next, I'm splitting it into the test and train. Why am I splitting this? Because I do not have the test data separately. So I don't want the model to know what are the actual labels for the test data set, right? So that's why I split it into X test and Y test and Y train using this train test split. So it basically takes the entire data set, and 80% of the entire data set becomes training data, and the remaining 20% is used as the test data. So over here, I am creating a model known as the k-neighbors classifier or the KNN model, and I'm setting the parameter, the hyperparameters neighbors or k as 3. Okay, next I'm fitting the training data, and then I'm passing in the test data to make a prediction, and I'm storing all that into the variable ypred. Okay, so now I'm calculating something known as the accuracy using the accuracy score function. So basically, what does accuracy do? It basically checks how many of those predictions are correct. So like how many of my predictions are actually correct when compared to the true predictions. So that's what accuracy does. So when I run this cell, I get the value as 97% accuracy. That means 97% of these predicted values are correct. So that's cool. That's very nice. And also this cell will take a long time to run. Even this cell, when you get the data set, these two cells, obviously it takes a long time to run. This cell will take a long time to run. This cell, like I just said about the time complexity, it takes a very long time to run. Okay, so now what if I increase the value of k to say 50? Okay, so over here the accuracy, you can see it decreases. It's 96.3, so it decreased. What if I take k as 25? Then it's becoming 95. So you can see that it's decreasing when I increase it to these values of k. I didn't try any values in between these, right? So I'm not interpolating anything. But yeah, so 3 was a good k value. Now let's take the value k as 5. So what happens when I take k as 5? I'm getting the accuracy around 97 only, though 3 was higher. So this model, I mean, this algorithm exactly behaves like the quote, you are the average of the 5 people you surround yourself with. Like you behave like those who you surround yourself with. That's essentially how this algorithm behaves. Okay, so now I got some accuracies. Now I want to see where exactly it's going wrong. Okay, so I can use something known as a confusion matrix to plot this to see where exactly it's going wrong. Okay, so you can see this is the code to plot the confusion matrix. So what is the confusion matrix over here? So it basically takes in it basically just plots the predicted labels and the true labels. It basically plots a plot between the predicted labels and the true labels. So essentially what this means is this 6 you can see over here, right? So that means that the model predicted 6 images to be of class 0 when they were actually class 9. So this is the actual class and this is the predicted class. So they were it predicted it to be 0. I mean, I predicted for 6 images the value, the number as 0 when they were actually 9. Okay, so even over here, there's 17, a very high number over here. So that means it predicted 17 images to be of class 7 when they were actually of class 2. So obviously, clearly, the more colorful these diagonals are, the more better it is for us. Or the higher number these diagonal elements have, the more better it is for us, because it's predicting 9 when it's actually 9, obviously. And this is doing a pretty good job. It has 97% accuracy. So here and there, you can get some problems. So that's about the implementation of the KNN algorithm. So all the code part. Yeah, okay, now I'll share the attendance QR code to scan it, guys. Okay, so scan the QR code. And you guys can also ask some doubts if you have any. Scan the QR code and fill in the attendance, guys. Guys, do ask up, raise your hands, or text in the chat if you have any doubts, and fill in the attendance form as soon as possible. Okay, so some of you guys are asking the importance of the K, right? Of the number of neighbors you consider. So essentially, K determines the decision boundary between the two classes. If you choose a higher value of K, you cause underfitting. But if you choose a lower value of K, you cause overfitting. So that's why you have to choose a proper value of K to balance underfitting and overfitting, and to make a proper decision boundary so that the model even generalizes well to unseen data. K and the distance metric are two hyperparameters, and both of them play a very important role in determining the model's accuracy. Okay, guys, with that, I'm done with the session. If you guys